Hello, hello, AP Calculus BC. I bet BC students, you're finally happy to be acknowledged since I kept saying AB. But there's more videos that overlap, right? We have something like 8 or 9 AB and BC videos, and you guys only have about 4 that are specific to BC. So this is the very first one of those. This should be about the 5th or so in your series of videos, the first 4 being all AB topics, but I think this one fits in really nicely after you do the AB particle motion because we do more particle motion today. So this is actually a pretty long video, and I may end up splitting it in half depending on how long it takes me to get through it, but we'll do our best. I found that although there are a lot of problems asked, it actually goes pretty quickly, so we'll see. Might be split into 2 parts, might be into 1. This first part, though, without a doubt, is going to focus on parametric and vector-valued functions. Remember that parametric equations are 2 separate equations written as x of t equals something and y of t equals something else. So they're split apart into 2 separate, we call them components, one telling you how the particle is moving left or right, that's x of t, and the other telling you how the particle moves up and down. With parametric functions, you need to be comfortable finding dy dx and the second derivative, or how y changes as x changes. Dy dx is pretty easy, and we're going to do the same thing multiple different ways today. We just take the derivative with respect to t of my y equation, and then we divide that by the derivative with respect to t of our x equation. All right, our derivative is going to have t in it as the independent variable. Well, what about the second derivative? This one's a little bit trickier here because we don't want to treat this as 2 separate pieces. Rather, we want to treat the second derivative as analyzing how the first derivative changes. And how does the first derivative change? Well, that's d dt of the first derivative. So d dt of basically that answer over there. Let's make sure that's a t. But then we want to see how the first derivative changes as x changes. So we need to divide by d dt of our x equation. So that is a pretty tricky one there. You'll want to commit that to memory, but then I think you'll be okay. The last thing you need to be comfortable with for parametric equations is how to find the length of a specific arc. And that's something that we first saw with non-parametric equations, right? And with non-parametric equations, I'll remind you right now, it's the integral from a to b of 1 plus the derivative dy dx squared dx. With parametric functions, and that is based off of the Pythagorean theorem, with parametric functions, because we have 2 separate derivatives, we essentially do the same thing. It's just the first derivative with respect to x squared, or I'm sorry, with respect to t. So the derivative of the x component squared plus the derivative of the y component squared. Lastly, we're going to deal with vector-valued functions here. Vector-valued functions are functions that are written as a vector where you have 2 components, and you might be saying, well, isn't that the same as parametric equations? And yeah, for all intents and purposes for this class, they are the same. Usually vectors are written with little arrows and pointing in a direction, so on and so forth. But it's actually a little bit easier than parametrics because if you're asked to find, let's say, so this would be in terms of our particle motion, this would be the position of the particle. If you're asked to find the velocity, well, it's easy. You just take the derivative of each one separately, d dt of each one. It's kind of like if you were to take this and put one here and the other over here. And then if you want the acceleration, take the derivative again. There's only a couple things that are a little different here. Speed is still the absolute value of velocity. However, because velocity has 2 components, so speed is still the absolute value of velocity, and let's pick a time value. Let's, I don't know, let's call it a here. In order to find the absolute value, we need to remember that the absolute value measures the distance from 0. This position out here is going to give us 2, so if you think of an xy axis, it'll give us a point that has both x and y components, or both x and y velocities. To find the distance to 0, it's the Pythagorean theorem, and so we write it as the square root of the first derivative, and we'll use a because we should be evaluating this at a number here, plus the first derivative of y, I'll need a little bit more room, also squared. So if they ask you, what is the speed of the particle at 3? Well, you just do this over here. Now, realize that if you only had one component, right, because last class you talked about particle motion that only had one of these guys, one-dimensional particle motion instead of this two-dimensional, well, then it's actually the same thing, right? It'd just be the square root of, there's only one component now, so it's x prime of a squared. And that will essentially cancel. It'll give you a positive answer, though, because of the square root, and it'll show you that the absolute value of velocity is just the derivative of velocity. So if you're dealing with just one dimensional, or we call it rectilinear particle motion, then you should be just fine using the same formula, just use one of them instead of two different components. Be careful comparing that to total distance. Total distance is just like arc length, and it's going to be the same formula that we had up above. So total distance involves an integral from a to b, and I'll write it the same notation that I did down here. It's going to be x prime of t squared plus y prime of t squared dt. It is the same formula as arc length from up above. So they're very, very similar. Usually you will get a free response question on either parametric or vector or polar functions. One of those three usually shows up as one of the three BC free response questions. In fact, we haven't really talked about that yet because we haven't done a BC-specific targeted review, so let's take a minute or two to discuss what the BC exam looks like. 2/3 of the BC exam is AB material. You might even have some of the same questions as those of your friends who are in AB. Not necessarily all the same, but you might overlap on some. And you will overlap on 3 free responses. So if you ask your friends who took AB what their free responses were, you will recognize 3 out of the 6 of them. Because on your BC exam, you get 2 different scores. You get one score where they only score the A-B questions. So they look at the multiple choice, they take the 2/3 of those, it's about 30 questions, they take the 30 A-B questions and 3 free responses, and they give you a score there. That's called your A-B sub-score. And so that actually serves as a score of how you would have done on A-B. So even if you don't do well on BC, if you do well on that part, that can either replace your AB score if you took it a year prior, or if you don't do well on BC, you can just submit your AB subscore and say, well, at least I passed AB. I get 1 semester of calculus, but not 2 in terms of college credit. There is a second score, though, that is your BC score. The BC score isn't just the BC questions. The BC score is everything put together, all 45 multiple choice and all 6 free responses, and that's scored like a regular AP Calculus exam, and that is your overall score for BC. If you get a 3, 4, or 5, most schools will consider that as passing both semester 1 and semester 2 of calculus. In the weird, rare occasion that maybe you get a passing score in AB, or in BC, but you don't in AB, just submit your BC passing score, and that gives credit for both semesters. So, jumping back to the free response, 3 questions are AB, which is why you're doing all those videos on AB calculus, and then 3 of them are BC. What will those topics be? That's a little bit tougher to predict. Usually one of the 3, usually the very last question, question 6, is on infinite series. So you're going to expect one of those on, your infinite series, your maybe Lagrange error bound, anything like that. A second one of them is usually on parametric, vector valued, or polar functions, which is what we're focusing on today. We'll do polar at the end. And then the third one is kind of a wild card one, and so we'll discuss some other possible options of that third one later on. But if you can predict 2/3 of the free responses, at least on the BC side, you're in pretty good shape. Okay, let's get back to this. Many of these problems, I think 2 out of the 3 free responses for parametric and vector valued are going to be calculator active, and one of the 2 polar will be calculator active as well. So let's get to it. This comes from 2016. At a time t, the position of a particle moving the xy plane is given by the parametric functions x of t comma y of t, where they give us the derivative of x, and they give us the graph of y. All right, at the time t equals 0, the particle is at a position 5, 1. We can actually see that too, right? At a time of 0, we can see that the particle is at a point of 1, right? 0, comma 1, that's what it means right there. Okay, so find the position of the particle at a time of 3. Well, part of that's really easy. We know that our final position, I'll kind of do down in the corner over here, is something comma something. So at a time of 3, what is the x, what is the y? Well, the y is easy because they gave us the graph of the position for y. So if you're looking at a time of 3, we just need the y value, which hopefully you can tell is -1/2. Woo! Halfway done. However, the x is a little bit trickier because we don't have a graph of x. We do have a derivative, though, which is kind of nice. And we should be comfortable manipulating this derivative to find position, right? This is just like particle motion. We're just doing one-dimensional just with the x. So the position at 3, so I want to know when the particle is at 3, and I know at 0. So we're going to do the antiderivative of dx dt with respect to t. And I know that that's going to be, using our position notation up here, x of 3 minus x of 0. Moving this around a bit, we're looking for x of 3, so I can see that x of 3 is equal to x of 0 added to this integral from 0 to 3 of dx dt. Working this out, x of 0, they told us the position of the particle is located at 5. This guy is just an integral. And to save some time, I already loaded all of my calculator active equations into my calculator. So if you haven't done that yet for here, you should probably turn on your calculator and load these in. But I'll show you over on this guy. Here is the equation to which we're referencing right here, right? And so that's an f1 of x. So all I need to do is menu calculus integral. We're going from, I think, 0 to 3. And it's of f1 of x dx. Let's make sure I didn't lie here. It might have been 5. Nope, I was right. That's good. And it's 9.377. 9.377. And when you do the math, adding everything together, you're going to find, I'll need a little bit more room here, that this is 14.377 plus whatever else comes at the end. And that's it. Position of the particle at 3. Not bad at all. Find the slope of the line tangent to the path of the particle at t equals 3. Well, slope of a tangent line, that is always, always, always dy dx. All right, and dy dx in terms of parametrics is going to be d dt of the y function divided by d dt of the x function. And we're actually going to do a couple things at once because we know that this is also going to be evaluated at t equals 3, don't we? So evaluated at t equals 3, I'll use this extra notation, evaluated at t equals 3. All right, well, the slope of the y function at a time of 3, here's a time of 3, the slope of that function, that's up 1 over 2. So the derivative of y evaluated at 3 is the slope 1/2. dx dt evaluated at time equals 3 is just this guy evaluated at 3. So we can actually find that on our calculators really quickly, right? We can just do something like f1 of 3. And we get sine of 27 plus 9, which you can keep on the free response. If you want to do that instead of writing decimals, that's completely acceptable as a response. But I'm going to go ahead and do the approximation, 9.956. 9.956. And then we just have to do 1/2 divided by that guy, and I've prepped it already. It's 0.05021, whatever you want to do. And we're set. There's the slope of our tangent line. Not bad at all. Moving on. Find the speed of the particle at 3. We got this. We just went over this earlier, right? Our speed of the particle is the absolute value of velocity at 3. And to do that, we're going to go ahead and I'm going to, instead of doing the dx dt, I'm just going to write it as x prime of 3 squared plus y prime of 3 squared. All right, x prime of 3 squared is, I'm going to do all that in my calculator, but y prime of 3 squared, we know y prime of 3 from earlier, that's 1/2 squared, right? So I'm going to do x prime of 3 squared, and we're just going to put this all into the calculator at once and call it a good day. So this looks like so. We have our control, square root, and then we had, we'll need some parentheses here, I think. So we have f1 of 3, and then second set of parentheses, squared, plus, and 1/2 squared I'm pretty confident is 0.25, so we're set there. We got our answer, 9.968. 9.968. There's an extra 9 if you wanted to round it. And we're good. Last one. Told you these went quickly. Find the total distance traveled by the particle. Well, that's actually very, very similar to what we did up above. I find that students tend to confuse C and D. Well, I know on C, speed is a part of velocity, so I want to keep velocity as it is. Distance, though, has to do with position, and that's the antiderivative of velocity. So this one can be a little bit trickier here, at least I found it to be a little bit trickier. So we're going to go ahead, and in order to find the total distance, we're going to have to go from 0 to 2, and we have the square root again of x prime of t squared plus y prime of t squared. Now, the reason that this is a little bit trickier is because y prime is not constant. Right? If I look up here and I think about all the slopes, in fact, I'm going to take a quick second and write the equation for y prime of t just so it helps us out, right? So I'm going to say that y prime of t equals, let's just find all the slopes of these lines. From 0 to 1, right? So from 0 to 1, it looks to me like the slope is down 2 over 1, or -2. Okay, and then from 1 to 2, 1 to 2, I probably shouldn't put equals since there's sharp points there. From 1 to 2, it looks like there's a slope of 0. And then from 2 to 4, no equals all the way through. There we go. From 2 to 4, it looks like the slope is up 1 over 2, 1/2, right? So we have all those, but the problem is we're integrating from 0 to 2. And so I see two different derivatives. I think to deal with that then, when I do my integral, I'm actually going to split this into two parts. I'm going to do the integral from 0 to 1 of the square root of x prime of t squared plus, and we just saw that the slope of y prime there was -2. Then I'm going to do the integral from 1 to 2. We have our x prime of t squared, and we saw that the derivative of y from 1 to 2 was just 0. Once here, I'm just going to plug all of this into my calculator. And when you finish doing that, you're going to find you get 2.2378 plus 2.1120, and that gives you 4.3498, so on and so forth. And there is our total distance. All right. Moving on to our second parametric or vector valued function, we have another calculator active problem from 2010. I tried to pick these so that they had some different questions, but you'll find that A and B are pretty darn similar to what we did before. I think you guys will be just fine with those. As before, though, I already put in dy dt into my calculator. I think at some point I'm probably going to need x prime, right? They give us x of t, but I'm going to state, and I'll write this as dx dt, and you can write it as x prime. We know exactly what you mean. That's going to be 2t minus 4, right? So just having both of those might be useful. Okay, find the speed of the particle at a time t equals 3. Well, we know speed is the absolute value of velocity, and so what we're going to find here is this is going to be the square root of, and then it's just going to be x prime of 3 squared plus y prime of 3 squared. And when you do your math, it's nothing too terrible at all. And you have a calculator really to help you out too. You're going to find that that's 2.8284. All right, no sense in spending extra time on the calculator there. You should try it. Make sure everything worked out. Make sure I didn't make a mistake, but nothing bad. And then total distance, very similar as well. Just getting you that practice in, right? Integral from 0 to 4, square root of, and then this is just going to be x prime of t squared, right? We want to make sure there's a function here, and y prime of t squared dt. Put all that into your calculator. It's calculator active. You'll get 11.5876. All right, but now we get to the new stuff. Find the time t where the line tangent to the path of the particle is horizontal. Is the direction of motion of the particle towards the left or the right at that time? Well, let's break that down. First, let's start with where the line tangent to the path of the particle is horizontal. What causes horizontal tangents? Oh, that's when the slope, or dy dx, is equal to 0. So we should probably start by finding dy dx, yeah? Dy dx, we know that that's going to be d dt of y divided by d dt of x, but those are just fancy ways to say the derivative of y, which we have. That is our te to the t minus 3 minus 1, and then the derivative of x, 2t minus 4. What would cause this derivative to be equal to 0? Well, if this is going to be equal to 0, then that is when the numerator becomes 0. So we're going to set this equal to 0. That's going to imply that te to the t minus 3 minus 1 equals 0. And how do we deal with that? Oh, we just graph it and find the zeros. No reason to solve here. If you have a CAS calculator, you can run your solve function. I, again, already have this set up, though. I'm going to turn off f1 of x, though. And then I have the second one into f2 of x, but my computer decided to run wild there. That was awkward. Third tries the charm. Go up, please. No, not forever. May have to bring the mouse in. Ah, so frustrating. Okay. Here we go. Be faster in the long run. Gave you guys time to catch up. So we are going to go through, and we are going to actually go to the right spot this time. And I'm going to go to f2 of x, turn that on, and I see one spot where we cover or we cross the x-axis. Menu, analyze graph, we want that 0. The 0 is somewhere in here. I'm just on the struggle bus today. There we go. I don't trust that decimal. I'm going to give more decimal places there. And because I'm probably going to have to use that, I'm even going to store this for later on. So I'm going to click once and then Control Store. We'll just call it A, and we should be set. Great. So we now know that when the particle is, or when there is a tangent line to the path of the particle, a horizontal tangent line, that occurs at a t value of 2.20794, so on and so forth. And my curly braces were not pretty there. Awesome. Now what? Well, now we need to figure out which way the particle is moving at that time. Now notice that we actually have two different equations that tell us how the particle moves. My velocity is technically given by a vector of x prime of t and y prime of t. Each of these components works together to show how the particle moves. So, because we're talking about this time value, let's go ahead and figure out what each of those are at that time value. So what is my velocity vector, 2.20794, at that time? Well, I'm just going to find each of those. We know that x prime of t is going to be pretty darn easy, right? X prime of t was just our 2t minus 4, so I'm just going to do 2 times a minus 4. There's my first one. And then let's also do y prime of t. I have that equation buried in f2 of, and then we're doing it in a, right? Okay, and we're there. Oh, that one said it was very, very small. All right, now let's talk about that very, very small for a quick second. If you ever see something like this, and you'll see it on the 84 more often than the Inspire, what this really means is take the decimal place and move it 14 places to the left. So really this is negative 0.000000004, right? So essentially that means 0. So if you see this on the 84, think it means 0. If you see it on the Inspire, it means 0. Why would we get 0 for the y component? Oh yeah, because we just saw on this previous page that the y component is this top part, and we just found the value of time that makes that 0. So what's happening at this horizontal tangent? Well, it's telling us that the particle is not moving up and down at all, right? It's frozen in the up, down, the vertical direction. However, in the left-right direction, we got 0.416, which means when our tangent line is horizontal, the particle is moving which direction? This is just like last class. Because the derivative is positive, just this number, that's all we need to look at, that means we are moving to the right. This is 0, which means we're not moving up or down. If you had gotten, like, let's say a negative answer here or something, 2.174, I'm just making it up, that would mean we're moving down. What happens if you move to the right and you move down? Well, then you're moving diagonally down overall. Those two components combine together to push us downwards diagonally. But this is 0. They asked if the particle is moving left or right. We found because this is positive, we're moving to the right. Justification, as x prime of 2.207 is greater than 0, the particle moves right. All right, scooting on down. There is a point with an x-coordinate 5 through which the particle passes twice. Find each of the following. First, the two values of t when that occurs. Okay, well, if this is the x-coordinate, then I think we have an equation that tells us the x-coordinate of the particle, which I just skimmed by. They told us that x of t is t squared minus 4t plus 8. I think if we want to determine where the x-coordinate is 5, let's just set that equation equal to 5, right? So we just have t squared minus 4t plus 8, and then we need to solve. Well, there's two ways to solve. You can graph each equation and find their intersection, but because I've done this problem before, I actually know that this one factors, and so I'll just take a quick second and factor it, just reminding you that there are a couple ways, even if you don't have a calculator, to solve this. Multiplies, adds, excellent, so we find that t is both 1 or 3, and that is when the particle has an x-coordinate of 5. Then they ask us to find the slopes of the lines tangent to the particle's path at that point. Okay, well, slopes, that's just our dy dx stuff, right? And so we've done this before. One of them is going to be dy dx evaluated at t equals 1, and the other is going to be dy dx evaluated at t equals 3. How do we do each of these? Well, it's going to be our dy dt evaluated at t equals 1. That's the equation I have in f2 of x, over, and then the other one was that, 2t minus 4, right? So 2 times 1 minus 4, and you'll do the math. Same thing over here. We need to find dy dt evaluated at t equals 1. And then we also need to, 3, there it is. And then we also need to find 2 times 3 minus 4. However, I've done both of these before. This one ends up being 1. It's a nice number. It's wonderful. The other one, though, is much less nice, and it's 0.4323, so on and so forth. Just use your calculator. All right, third one. Find the y-coordinate of that point. Okay, well, that's interesting. So there's an x-coordinate 5 through which the particle passes twice. So what is really happening here? Well, if you have an xy axis, we found that an x of 5, I don't know where this is, but essentially what's going to happen is this is going to come up, and then who knows, maybe my graph looks something like this. So my graph is passing through this point twice, which means this is certainly not a function. That's like the complete opposite of what the vertical line test tells us should happen. We don't know exactly which way it's looking like. I don't know what the graph looks like, honestly, but it's passing through twice. Regardless, though, that means that our y-coordinate is, of course, the same each time. So how do we find the y-coordinate? Well, as always, this has just got to be our fundamental theorem of calculus. There are actually two different ways you can do this as well. They gave us y of 2, right? They told us what the y-coordinate is at a time of 2. So I know that when I integrate, I'm going to include that 2 as one of my limits of integration. What else am I going to include? Well, what am I trying to find? Well, the y-coordinate at this point is either found at a time of 1 or at a time of 3. So we can either integrate time of 1 or a time of 3 is going to give us the same y. So we can either go from 1 to 2 of y prime of t dt, or we can go, the other thing we know is 2, right? Or we can go from 2 to 3 of y prime of t dt. And so this would give us y of 2 minus y of 1. Or on the other hand, you'd get y of 3 minus y of 2. What am I looking for? Well, in this top equation, I'm looking for where is y located at 1. In the bottom one, I'd be looking for where is y located at 3. We already said they're in the same spot, right? That's right here. So those should give us the same answers. And in fact, I've done this several times. They do give you the same answer. And if you use a non-rounded value, so if you use this exact, and I shouldn't do it there, I should do a different color, huh? If you use this exact value for y of 2, once you manipulate everything, you're going to find that y of 3 gives the same value as y of 1, and they actually give a very nice value. They give a value of 4. Ta-da! All right, last parametric equation question. We're given two parametric equations. This is a no calculator question, and they're asked to find the following derivatives. Full disclosure, I may have made this problem up to test you on other things. I couldn't remember where it came from. But let's find some derivatives. So dy dx is going to be d dt of the y equation, which is t squared plus t, divided by d dt of the x equation, natural log of t. This gives us 2t plus 1 divided by 1 over t. And although it is okay to leave like that, I would probably suggest multiplying top and bottom of the fraction by t to get 2t squared plus t. All right, what about our second derivative? Well, the second derivative is again found by saying we want to look at the change of the first derivative, which is what we just found, divided by how x is changing. So what does this look like? Well, we're finding d dt of the answer from the previous problem divided by d dt of my x equation, which was natural log of t. And so that gives me 4t plus 1 divided by 1 over t. And if we again multiply by t, because why not? Easy enough, 4t squared plus t. All right, part B. Write the equation of the tangent line in the form of y equals f of x to the curve C when x of t equals 0. Okay, well, if it's y equals f of x, then we know the general form of our tangent line, not surprise here, is y equals, we'll leave the slope blank, it's going to be x minus something plus something. How do we notate these, though? Well, the something and the something come from this guy over here. They need to be at some value of t, because they told us when x of t is 0, so I know that this guy is going to be 0. The x coordinate is 0. That's what they're telling us here. But I don't know the time. So maybe a brief pause. If I know that the x component is 0, don't we have an equation for the x component? I think our equation for the x component is natural log of t. So I think if I set 0 equal to the natural log of t, that will tell me the time that causes x to become 0. We do need to do e to the power of each side. Not quite sure why I put the little caret there. These undo each other, and we find that t equals 1. So really they asked us to write the tangent line that occurs at a time of 1. At a time of 1, x is 0. We can find when y, or what y is at a time of 1. And then we're also going to need to find dy dx evaluated at a time of 1. Well, it's pretty useful that we did part A, because, hey, look, we know dy dx, so if I want to find dy dx evaluated at a time of 1, it's just going to take this guy. 2 times 1 squared plus 1. 2 plus 1 gives us 3. So we know this will be y equals 3 times x minus 0, that's just x. Plus, what about the y value? Oh, well, we have the y equation as well, t squared plus t. So we know to find y of 1, that will just be 1 squared plus 1, which is 2. And so we have our tangent line. Tricky question because they didn't give us the time it occurred, which we needed. So we had to find that time first, and then it's just a matter of evaluating the other equations there. All right, use your tangent line to approximate the y-coordinate of the curve when x equals e. Will your approximation be an over or under approximation? Okay, well, as we go through with this one, right, we're going to find the y-coordinate, when x equals e. And that's useful because they gave us an x value. That's actually really nice that we have a tangent line, because our original equations up here are in the form of t. So if they said when x equals e, then you'd have to do a little solving, which could be obnoxious. All right, so we're going to say the y coordinate is approximated by 3 times, we're using this tangent line, 3 times e plus 2. And in fact, I'm going to stop there because I don't have a graphing calculator. So I'm saying the y coordinate is 3e plus 2. Okay, will this be an over or under approximation? That's a little bit trickier. I think maybe we can go through and we can figure out the concavity of our curve, right? Haven't we done something like that before, where the concavity of our curve is, if it's concave up, the tangent line's an under approximation, concave down, the tangent line's an over approximation. So yeah, let's try to do that. Let's find the second derivative, d squared y over dx squared, evaluated when x equals e. But unfortunately, I think our second derivative is in terms of t. Well, that's a little frustrating. Could we use the fact that x equals e to find our time? I think so, because we know our equation for x of t is natural log of t, and they told us when x is e. Couldn't we solve this? I think to isolate t, you do e to the power of each side, so I think actually e to the e will be my time. That's pretty crazy, right? E to the e power, 2.7 something to 2.7 something. That's still a number though, right? 3 to the third is 27, so 2.7 something to itself has got to be less than 27, but I think greater than 4. Bit of a range, but either way, there's our time value. That allows us then, I think, to find this second derivative at e to the e power. Okay, as we go through, we saw up above that this is 4t squared plus t, 4t squared plus t. All right, and you might look at that and go, whoa, that's the craziest math I've ever seen, but I'm pretty confident about that, and that is greater than 0. Okay, so how do we conclude with this? Well, as d squared y over dx squared is greater than 0, I should probably say at time equals e to the e, then the tangent approximation, what does it do? Let's see, greater than 0, that means concave up, the tangent line's below, is an under approximation. Nice. Not too bad, right? A little tricky there, kind of some weird values, but it works. Set up but do not evaluate an integral to find the length of the curve from 0 to e. Well, we've done this before, haven't we? The integral from 0 to e. The length of the curve, that's just, I think a way to find the total distance, right? The square root of x prime of t squared plus y prime of t squared dt. This wouldn't fly, I think, as a final answer. We would probably want to replace x prime and y prime. It might be okay, but since we already know those, right, x prime of t was just 1 over t, and y prime of t was 2t plus 1. We had to find those earlier, didn't we, up here? So you might as well put those in and then throw the dt at the end. And we're done. So take a couple minutes, jot down some important tricks you need to be successful on these, right? You can reference back up top here, not bad at all. And then once you're ready, you can unpause and we will go through our polar section as well. Ready, set, go. Welcome back, and we're still on this same one. Again, I know it's a little long, but I think we'll be okay. We're going to polish this off with 2 last free responses on polar functions. There's a couple things we need to be able to do with polar. First, you'll need to know the difference between dr d theta and dy dx. I find a lot of students confuse those, right? So if we looked at a sample equation, right, like r equals 2 sine of theta, if I wanted dr d theta, that means I would just do d theta to each side. Can we see that this left side becomes dr d theta? Right? And the right side isn't bad because everything is already in terms of theta. It'd be 2 cosine of theta technically times the derivative of the inside, but d theta of theta is just 1. So that's it. So when they ask for dr d theta, they just mean take the derivative of your original equation with respect to theta, which is just like an original derivative. dy dx, though, is trickier. dy dx is like our slope of a tangent line. And so it is very, very similar to parametric equations where it's y and x, but now it's not d dt anymore because our independent variable is theta. It's d theta of each of these. And I don't have this next part fully memorized. I really don't. But if you're asked to find this, then you need to remember a couple things. First, you need to remember how to convert between polar and rectangular. In particular, y is r, think the y-axis, that's cosine, nope, that's a lie, that's sine, r times the sine of theta, right? Sine's in charge of the y-axis. Divided by d theta, how do we convert x? Well, that's r times the cosine of theta. And then from here, because we're not quite done, you have two options. Option one is you can replace r with the equation given to you in the problem. So you could say, ooh, r is this, and you could plug it in. Sometimes that makes our derivative overly complicated, so I prefer not to do that until the very end, but some students have success there. What do? I actually take the derivative of this right away. Now don't forget that our derivative has two functions multiplying, which means we have to use the product rule. d theta of r is dr d theta. We just talked about that derivative up at the top. And then d theta of sine of theta is pretty easy. However, with the product rule, we keep that the same to start, right? And there's always a plus in the product rule. We keep r the same, and then the derivative of sine of theta is cosine of theta. It's not bad. Good practice for your product rule. Same thing for the denominator, right? We know, we'll do the same colors here, why not? We do the derivative of the first one first. We keep the second one the same. And then you're going to want to put a plus, but because I've done this so many times, I'm going to hold off and show you why. R stays the same. The derivative of cosine is negative sine. However, I just like to move the negative out to the front, and then you end up there. This is not something I'd suggest you memorize. It might come up one time somewhere on the AP exam, and I say might because it does not come up every year. If it does, then start here and work it out using the product rule. I don't suggest you memorize it unless your brain has a lot of empty space and you're like, no, I can just cram some more stuff in there. Then sure, throw it on a formula sheet that you want to memorize. Okay, but remember, there is no formula sheet on the AP exam. All right, what else do we need to do with polar? You need to be able to find the area of a graph, and that's the one we derived a while ago. So it's going to be from something to something else, and it's 1/2. And then what? Do you remember? R squared d theta. Now, when I say r squared, this is actually an equation, right? So if r was 2 sine of theta, that's what would go in there. Yeah? So sometimes you'll see people write that in a different way, but either way, I like to. Sometimes I'll write it as f of theta instead of r, but I just put it that way. And if you want to find the area between two polar graphs, it's nothing too bad. It's just the two areas subtracted together. And I'll do r1 to represent the outside area minus the integral from r2 squared d theta. Let's go ahead and get started. No calculator for the first one. The graphs of the polar curves, and I'm going to highlight these in red, show r equal 4, and this is where things come in handy if you paid attention to our polar unit. R equals 4, we need to know is a circle with a radius of 4, right? This is going to allow me to trace the correct r equals 4. Sometimes students are like, wait, is this whole outside thing? No, it's right there. Okay. Then we have the second one, which is r equals 3 plus 2 cosine of theta, and that's this guy over here. All right. Now they're very nice to you, and they told you when these intersect. They intersect at pi over 3. So pi over 3 is this guy right here. And then they also told you that they intersect, and it's kind of a big long guy over here, at 5 pi over 3. Very nice when they do that. If they didn't do that, you would have to set each equation equal to each other, solve and find those, and it's doable, but it's definitely going to save you time if you didn't, or if they give it to you. All right, moving on to part A. Now that we've set everything up, we are going to go through and find the area of R, which is that shaded region inside the red circle, but outside the blue cardioid there. And we just need to write the expression. We don't actually have to find it. Well, the places of intersection are going to be super useful, right? If I did the red circle from pi over 3 to 5 pi over 3, and I'll try to fill all this in, right, it would be all of that, right, which is clearly too much. We need to subtract out the places that I'm going to do in blue right here. We need to subtract out this, which is the interior of the cardioid. So what do? Well, we find the larger area, which is that red area, and then we subtract out the smaller area. You can think of it as the outside function minus the inside function. So we could do it as two separate integrals. We could do the integral from pi over 3 to 5 pi over 3 of 1/2 my equation for the red circle, which is 4 squared d theta, minus, and then my other integral in blue, still from pi over 3 to 5 pi over 3, 1/2, that is 3 plus 2 cosine of theta squared d theta. If you wanted, you could also put this all together. You could notice there's a 1/2 in common. They also have the same limits of integration. And we could do it as something like this. We could factor out the 1/2 integral from pi over 3 to 5 pi over 3. And then 4 squared is 16, right? Minus, and actually, no, let's keep it 4 squared just so I can make a point, minus 3 plus 2 cosine of theta squared d theta. Either of those would work. Two things to note about this condensed integral over here. First, some people say, well, don't you need like an extra set of parentheses over here? And in a normal problem, I would put those. I left those off on purpose just to show that you don't actually need those. The readers assume that this integral here starts the stuff, the integrand, the thing we want to take the integral of, and then the d theta stops it. So you don't need them. However, I do like to put those. And second, we also don't want to make one of the big mistakes I see people do with this, where they say, oh, both of these are squared. Couldn't I just rewrite this as 4 minus 3 plus 2 cosine of theta, all of that squared? And the answer is no, you cannot do that, right? We're not allowed to distribute or undistribute squares if there's addition or subtraction, so you do need to keep the squares separate there. Part B, find the slope of the line tangent to the graph of blah, blah, blah. Okay, well, we already know how to do this. It is dy dx. That's always the slope of our tangent line. And I'm going to cheat a bit. I found this earlier, so I'm going to use this again. In fact, I'm really going to cheat and see if I can just copy this one down. I think I probably can. We'll just take all that. Good. And I'm going to copy it and rewrite it down here, maybe. Paste it, and then slide it over. There we go. Good. That'll save me deriving and having to write it a couple more times. Okay, so what do we actually need to use here? And this is a dr d theta. Well, let's list everything important and then start substituting them in. We know that r is 3 plus 2 cosine of theta. We also are going to need dr d theta. So if I find that, dr d theta is just the derivative, so 0 minus 2 sine of theta, right? Derivative of cosine is negative sine. And then eventually we're going to need to substitute in pi over 2, so that actually might be useful as well. So not only do we have r, let's find r of pi over 2. So 3 plus 2 cosine of pi over 2. Cosine of pi over 2 is 0. I think that just becomes 3. And then we have, of course, dr d theta evaluated at theta equals pi over 2. That's because negative 2 sine of pi over 2. Sine of pi over 2 is 1, so we end up with negative 2. All right, I think we can go through and probably do this pretty quickly then. So we're going to find the value of dy dx evaluated at theta equals pi over 2. Well, dr d theta at pi over 2 we found is negative 2. Sine of pi over 2 is 1. Right? Can you see we're just filling in each piece here? R at pi over 2 is 3. cosine of pi over 2 is 0. So generally they choose numbers that cause half of this to cancel, either 0, pi over 2, pi, so the math isn't usually too awful. Dr d theta was again negative 2. Cosine of theta is 0 minus, and then we have our 3 again, and then sine of theta is 1. And don't forget, technically you are done right here. You can simplify this if you would like, right? It looks like the top simplifies to negative 2 and the bottom to negative 3 or positive 2/3. But don't forget, if you're pressed for time, you can stop here. And in fact, if you're really pressed for time and you wanted to go through and not even find sine or cosine of all of these, you could actually leave your answers like this. Right? So instead of negative 2 up here, you could, that was found by doing dr d theta, you could say it's negative 2 sine of pi over 2. And then the 1 comes from sine of pi over 2, right? It's a nifty way to get around not remembering what your trig functions are. Plus, and then of course you could do the rest. You can actually stop right here once you have all those in. Do you need to know your trig values? Yeah, because you can't use tricks like that on the multiple choice, but if you're short on time or you're not sure which way to go, then just leave it like that. You can do the same thing with natural log. Don't remember natural log of 1, just keep it as natural log of 1. You get full credit. Anything you can type into just a basic scientific calculator that has sine or cosine, full credit. All right, moving on. C, a particle moves along a portion of that same cardioid for 0 to pi over 2, right? So that's, we had that cardioid from before, and 0 to pi over 2 is just that part, right? It doesn't include the rest of it. Okay. The particle moves in such a way that the distance between the particle and the origin increases at a rate of 3 units per second. So I guess if it's really close, it's probably getting further away, right? Something like that. Find the rate at which the angle theta changes with respect to time and the instant when the position corresponds to that indicate units of measure. Okay. Whew. I'm seeing units per second. That's a DDT question. Because my original doesn't have t, I'm recognizing this as related rates. Oof, that's been a while. So how do we set up related rates? Well, we start with the rates that we know. What rate was given to us? We're reading through. The distance between the particle and the origin increases at a rate of 3 units per second. Okay, well, how do we call, or what do we call the distance between the particle and the origin? Well, take a look. I'm going to draw a bunch of these distances. Here's a distance, right? We just measure that straight line. Here's a distance. We measure the line. Here's the distance. We measure the line. In fact, couldn't we call this line r? In fact, r in a polar equation is the distance between a graph and the origin. So when they say the distance between the particle and the origin increases at this rate, what they're really telling you is that dr, the change in the distance as time changes, is 3 units per second. Okay, what else? Well, we also, when we set up our related rates, need the rate that we want, right? A related rates gives the rate we know and the rate we want. What rate do we want? We want the rate at which angle theta changes. Okay, so we want d theta dt, and this is usually going to be a when the position of the particle corresponds to pi over 3. So when theta equals pi over 3. All right, well, let's create an equation then. Do we have an equation anywhere that relates r and theta? Ignore the d, the dt, all that stuff. Do we have an equation that relates r and theta? Well, certainly. They gave us an equation. That's very nice of them. R equals 3 plus 2 cosine of theta. Excellent. All right, well, what else then? I think last but not least, we just need our derivative. Right? The derivative, actually this is the 4th out of 5 parts for our related rates, is found by doing d dt. We know that because of the dt's in our know and want of each side of our equation, the third part. So of r and of 3 plus 2 cosine of theta. So what is our derivative? Well, it tells us that dr dt is equal to 0 minus 2 sine of theta. Be very careful here. Times the derivative of the inside. I bet this is what most of us would mess up, because the derivative of theta is no longer 1. It is now d theta dt. Oof, tricky, tricky. Last but not least, we're on the evaluate section. Evaluate is where we take our derivative and we evaluate it for everything we're given. We know dr dt is 3, negative 2 sine. We know we're doing this at theta of pi over 3. And then we don't know d theta dt, but that's okay because that's what we're trying to find. So what do? We isolate d theta dt. Okay? So there's a couple ways to do it. The easiest, quickest way is to just divide everything off. And we say that 3 divided by negative 2 sine of pi over 3 is d theta dt. And I'm done. Now, if you did want to evaluate that and you wanted to check your work, it is negative 3 over the square root of 3. It takes a little bit of working to see that answer, but I would just stop here. It's a free response. Don't do extra work. Are we actually done, though? Didn't it say indicate units of measure? Units of measure are pretty easy for related rates. Just take the units that are on top and divide it by the units that are on the bottom. Units on top are radians per, and then the units on the bottom, dt, they told us already, second. Great. The end. I found that these polar equations tend to be pretty predictable. They usually ask something about the area of the graph. They usually ask something about a slope. Sometimes they'll say, where's the slope, horizontal, or just what's the overall slope? And then the last question or two tends to be that wild card, here's something random that you can't really predict, like related rates. So let's try one more, and then we're good for the day. Figure below shows that polar curve. This is calculator active. As before, I've already put these into my calculator just to speed up the time a bit. Let R be the region in the first quadrant bounded between the curve and the x-axis. So I'm going to do R in purple right here. And then S is the region bounded, so we'll do S in blue, between the two curves and the x-axis, right? All right, looking good. Cool. Find the area of R. Oh, they've easily slow pitched it to us. I love that. I should probably look at what these two equations are here. They told us that R equals 2 cosine of theta. I'm going to start with that because I know that graph. That is a graph, and I apologize. You can probably hear my dog in the background. He decided it's squeaky toy time. This graph I know is a circle with a diameter of 2 along the x-axis, right? That is going to be this guy. They only gave us part of it, right? This is what we call g of theta. Then I might as well, while I'm here, do my other graph, which is this guy, and this one right here is going to be f of theta. In fact, as we work through here, because this is calculator active, I'm going to avoid writing this name, and instead I'm going to write the name that they gave it, f of theta, much quicker than having to write all that out. Okay, so if we want the area of R, which is surrounded by that golden or that orange function, I think R is the only thing to do with the orange function, so all we need to do is just the integral from, they told us it goes from 0 to pi over 2. They were so nice to us here, of our formula, 1/2. Which equation? Just f of theta squared d theta. We're not subtracting anything. We're not doing anything weird here, right? We're just plugging all of this into our calculator. In my calculator, this is f3 of x. And so I'll show you what it looks like on mine just so you don't get confused by all that theta stuff. And then we'll check our answer. So we're going to go, actually I should probably double check that it is f3 of x, huh? Seems like a smart thing to do. So we'll tab up. We're going to turn, it is f3 of x. Very nice. I turn that one off. We'll go down. We'll turn that guy on. That guy on. They don't need to be on to use them. Okay, so you'll notice that I'm not also in polar mode. When I graphed those on my calculator, I was in rectangular. I think it's a little bit easier to do it this way. So menu, calculus integral. We're going from 0 up to, I think they told us pi over 2, didn't they? So there's two ways to do it. Pi is down here. You can do pi divided by 2. You can also just literally type in pi, wherever the p went. There we go, pi, and it knows that that means pi over 2 as well. Of 1/2 times, and then my function I said was in f3 of, and notice I'm using of x here. You can use theta. It just takes longer to get to theta right down there again. So I'm just doing f3 of x. It doesn't matter what variable, x, theta, q, pick your favorite, as long as they match here and here. And we find our answer of 0.6187315. Nope, that's not the right answer. because I forgot to square my theta, or my f of theta. Awkward. There we go. 1 here, 1 here. Let's throw the square on there. Second tries the charm. Whew, we did it. 0.648. Lovely. 648. If you want the extra decimals, it was like 414, something like that. And there we go. All right. The ray theta equals k. We'll do this one in black, I think. Theta equals k, where k is between 0 and pi over 2, divides s into two regions of equal area. Right, but do not solve an equation involving one or more integrals whose solution gives the value of k. All right, here's s. We're just looking at the blue area here, and what they're basically saying is there's going to be some ray out here that whatever theta rotation this is k, will cause this area down below to be exactly the same as this weird shaped area over here. I'm just guessing. It doesn't really matter where it is, and it's going to be somewhere between 0 and pi over 2. Well, how do we do that? There's really two different ways to do this. I'll give you both of them. It's up to you. But I think the key to it is understanding how do we find the area of S? We can't do the same thing we did over here with g of theta, because if I did that with g of theta, it would find all of this area, right? All of this area is, if I just use g of theta, I would need to subtract off the area from R. So what do I do here? Well, we can find the area, right, from 0. And just trust me on this for a quick second. I think it'll make sense shortly. We're going to go from 0 to k. That's the part that puts it, it cuts the area exactly in half. And let's just find the area of S from here to here. Right? Well, how do we do that? We do the outside function first, 1/2, and then the outside function was g of theta squared minus, and then the inner function, 1/2 f of theta squared d theta. I'm putting all of that into an integral at the same time. You could have factored out the 1/2 as well if you'd like. And what are we trying to do? Well, we're trying to find where this guy makes the two areas equal. I'm saying this is half of the area, and then wouldn't that be equal to the area from k to pi over 2? Right? My first integral gave me this area. My second integral is going to give me this area. And those integrals, I think, need to be equal to each other. So equal from k to pi over 2. We'll do the same thing. I'll factor out the 1/2 just to make this go faster. Same formula. G of theta squared minus f of theta squared d theta. Great. You might also notice that if you factor out the 1/2 from here, you can divide off the 1/2 from each side, so you could get rid of all of these. Right? You're saying the area from 0 to k is equal to the area of k to pi over 2, and that's fine. There's nothing wrong with that. Is there another way to do it? Of course, you could actually find the total area first. So the total area would be the area from 0 to pi over 2. Factor out that 1/2. G of theta squared minus f of theta squared d theta. That is the total area, right? Going from here all the way over to here. And we know that that total area has to be equal to half. Nope, wait, I lied. Well, let's just put in equals for now. We'll put an extra half in a second. Let's just do the area from 0 to k of 1/2. We should factor that one out front. G of theta squared minus f of theta squared d theta. Now be careful, because what I'm saying here is that the area from 0 to k is equal to the whole area. And that's not true. The area from 0 to k has to be equal to half of the total area. And that would be another way that we could set this up. Either of those are fine. Tricky question, but they are somewhat fond of asking a question like this on free responses. Where can we find half the area, half the volume, so on and so forth? We don't have to solve. That'd be much trickier. But yeah, I think that's about it. Let's move on to C. 2 problems left. For each theta, let w of theta be the distance between the points with the polar coordinates f of theta, g of theta. Oh, we need a visual for this. So w of theta is the distance between these 2 points. So if we jump back up here, what they're essentially saying is if you have a point, let's actually just use the ray right here, the distance between these 2 points is called W of theta. So this distance right here, W of theta, if you input a theta into our W equation, would tell you that length. Think about what's happening for the length. The length is pretty long here, and then it doesn't look like it's shrinking as I fill in those lengths. Yeah, I think actually until I get to pi over 2, it looks like it shrinks to 0. So I'm pretty confident W of theta is decreasing here, but that is what W of theta tells us. Okay, so W of theta is the distance. How could we write an expression for W of theta? Well, I hope so, because they ask us to do it. Isn't that just the outside function, which is G of theta, minus the inside function, F of theta, right? Because essentially what you're doing is you're taking this long ray to the outside function, that would be G of theta, that's the value of G of theta, and then you're subtracting off the ray to the inside function. So if you do the green one minus the orange one, it leaves you with the red function. There we go. Yeah, that's actually pretty easy to do. So there's W of theta. What's next? Find W sub A, the average value of W of theta. Ooh, average value. We should be decent with this. To find the average value, we know it's 1 over B minus A times the integral from A to B of W of theta d theta. Okay, we can do that. Right? We substitute that into our calculators. Nothing bad at all. So we have our 1 over pi over 2 minus, I'm just going to type out literally pi this time, pi over 2 minus 0 is just pi over 2. You could have even rewritten that as 2 over pi. That probably would have been easier, times the integral, calculus integral, from 0 to pi over 2 of, well, W of theta. Well, I think my G of theta is actually an F4 of x, so I can probably do this pretty quickly. F4 of x minus F3 of x. That's my G of theta minus F of theta. F3 of x. A nice little trick of the trade is if you're not sure which one comes first, you could always put it in absolute value, and then you'd get the right answer every time. But either way, we don't need to do that. So then we have dx at the end. Notice they even put in those parentheses. That was very kind of them. And they gave us an exact answer. How sweet of them. However, we don't need the exact answer. I'm actually going to go for the approximation, right? Control approximately 0.485. 485. If you want the extras, 446, so on and so forth. All right, cool. Using the information for part C, find the value of theta for which W of theta equals the average value. So they want us to set W of theta equal to 0.485, 446, so on and so forth. And I think in order to do that, we probably need the equation for W of theta, which was G of theta minus F of theta, wasn't it? And they're trying to see where is that equal to 0.485, 446? Well, we can solve this, right? This is all about graphing, isn't it? So graphing-wise, I'm going to go through, pull up my graphing screen. We should probably turn these two guys off. Notice this does not have to be in polar. It's actually easier if it's not in polar here, because although we're talking about a polar graph, realistically these are just equations, and we're trying to find a number. If we substitute it into one equation equals this on the other side. So I'm going to keep it in this rectangular mode. We were doing F4 of x minus F3 of x. And we want to know where is that equation equal to this guy. And to maybe save me a little bit of time, let's clear that out first. We're just going to copy this one down, be as accurate as possible. So we're going to store that as a, variable's already in use, rude. So if it's already in use, two options. One that I mentioned before, I'm just going to clear A to Z. And then we're going to try this again. Take that. Perfect. Now it's stored as A, so we'll go back to our other graphing screen. We're just going to graph y equals A, hit enter. We're only looking between 0 and pi over 2, aren't we? We're looking for a theta value, so I think it's just going to be this one value here. 1, 2, 3, 4, 5, somewhere in between 5 and 6. This is like 2 pi, here's pi, pi over 2, that's got to be the only one. So, menu, analyze graph. We're looking for an intersection, right? Analyze graph, intersection. There we go. And I don't trust that, so we're going to do a couple more decimals here. Looking pretty good. 0.517. Reading through the rest of the problem, they want to know something about my function, so I'm actually going to store this as well. So control store, I'll store this one as b, but it's 0.517. So theta equals 0.517, 688, something like that. Great. Some people say, well, wait, do you have to explain like what you typed into the calculator to get the answer? No, the AP exam expects to see a setup. What are you trying to solve? This is what I'm trying to solve. And then what is the answer? The process to find the answer doesn't use calculus, and they're testing you on your calculus knowledge. They expect you to be able to do the rest. Is the function f or w of theta increasing or decreasing? Well, I'm pretty convinced that just by the picture over here that w of theta will be decreasing, but they probably want a mathematical justification, so we can give that to them, right? The mathematical justification is we're going to find w prime of 0.517688, which is equal to, and that's going to be just g prime minus f prime if you want, g prime of that minus f prime of that. And luckily, that's something we can also do in our calculator. Very calculator-heavy problem here, but we're just about done, so we might as well get through it. Menu, calculus, derivative at a point. I'm doing number 2. And we're going to find that value, which I called b. And we need to do g, which was f4 of x. There we go, I think that's right. Minus f3 of x. Negative 0.581. That seems to make sense to me. So we find that w prime of 0.517688 is equal to negative 0.581859. So as w prime of that is less than 0, then w of theta is decreasing. Perfect. Yeah, definitely a lot to do there, but either way, you'll find that there isn't too much asked about polar. They tend to be pretty repetitious. They threw in 2 curveballs, C and D, that really had nothing to do with polar, honestly, besides being able to set up w of theta. The rest was just all average value and setting equations equal and derivatives. These 2 were tricky, but yeah, I find the area of polar is the most common. Sometimes they asked for the derivative of polar, and then the rest just brings in other knowledge. So thank you for hanging out through this video. I know it was a little bit longer, but hopefully you're able to get through it all and feel prepared, because this will almost certainly be one of your 6 free responses on the AP exam.